This works?
Yes, perfect. Thank you very much. Yeah, please start.
Okay, thank you very much, Fumiya, and hello, everybody. Long time no see. And today I would like to talk about some of our projects concerning about the robotic foot. And most of the workers were done by Chun-Yan Chen. He's my PhD candidate. And actually, he has got his PhD now. So I like to celebrate him by introducing some of his work to you. And these are the what we call biomimetic robotic foot. These three types I'm going to introduce. And before talking about the detail of the robotic foot, we have to understand that the complexity of the human foot. The human foot consists of the 26 bones. With respect to comparing to the very simple humanoid robot foot, normally it is a very flat plane, and they say that some of the medical doctors say that the structure of the bone will generate some moment to suppress the rotation of the body or to regulate the reaction force, for example. So that the structure will, embodiment will help to generate stable walking. So because the bond is basically making a kind of a structure with the ligament and the muscles. So it is very difficult to analyze overall structure. But instead, what we do is by constructing some of the mechanism out of the very complex structure, so that we can see what kind of contribution each of the element will generate. So we focus on several parts of the structure of the foot. First, we focus on the oblique joint existing. It is realizing by the virtual joint in the bone and in the bones. And the next one, we would like to focus on the subtalar joint. Subtalar joint is existing on the subtalar talus and calcaneus, which is generating the movement here. And this calcaneus bone is connected, this heel bone, I should say, is connected with the what we call plantar fascia. It's the muscle in the foot. And finally, we introduce what we call bevel gear foot, which is imitating the mechanism existing in the foot. So I'd like to explain one. First, I would like to introduce about this oblique foot. The structure of the foot is very complicated, but basically the concept is that we have a joint here, which is not parallel to the floor, but it's an oblique joint, and the movement of the foot is very similar to the movement of the real human, like this. So we guess that this kind of movement will generate a moment to suppress the rotation of the torso. And we realized some experiment. So this is actually the realized movement of the biped robot. And because the robot doesn't have any, how can I say, the frontal movement of the hip joint, but instead the robot only has the parallel motion like this. But instead, the robot has this oblique foot, which will generate the moment to suppress this yaw moment of the robot. And as a result, without any balance control, the robot can generate very smooth walking like this. And this is actually the result. And we put the force plate to sense the yaw moment. And we found that by using the oblique foot, we can suppress the yaw moment, which will generate the yaw movement of the torso. And after that, we change focus onto the subtalar joint with the plantar fascia. Plantar fascia is, as I said, the ligament connected with the toe of the foot with this the calcaneus, and this will generate very unique motion, as well as the oblique joint. It is supposed to generate the free moment to suppress the rotation movement of the torso. And this is the experimental result. This is also the bottom of the yaw moment will be suppressed by using the subtalar joint foot. And finally, we focusing about the mechanism to generate the motion of the forefoot and the ankle and the calcaneus, the heel bone. And they say that this motion can be assumed like a bevel gear, like this. And we just copy the idea into the mechanical structure like this. And this is actually a realized foot by using the bevel gear foot. And the motion is very, very interesting. And first, if the robot touch by the heel, then the heel is because the heel is a little bit offset outside. So if the one of the heel is touched to the ground, then they will generate the motion of the tibia, and the tibia motion will transfer to the motion of the forefoot, so that the motion of the structure, the foot is very complicated. And as a result, it will generate a natural motion to twist the tibia, if the robot touched by this heel. And then afterward, if the forefoot touches afterward, then it will support as a supporting structure to the motion, the body. So the robot stopped to generate the yaw moment, but afterward, then the heel release the foot, the forefoot structure will again generate the rotation, and the rotation will be transferred by the bevel gear again to the tibia, so that it will generate the rotation motion again. So it's a very complicated procedure. But finally, we could find that the robot can move forward like this without any balancing control, but it will generate the natural yaw moment to the robot. And these are the experiment results. We put the force plate beneath the robot and sense the yaw moment during the walking, not the stance, I should say, and found that the geared foot will suppress the yaw moment, obviously, with respect to the rigid foot. And so by constructing one by one the feet, and we can investigate about the effect of having complicated structure, complicated mechanism to support the robot without any calculation, any computation. So this is very good example of the embodiment to contribute to the stability of the motion. Thank you very much.